for today and for this week,
Yeah.
we have plenty of time because Atish could not make it because of the visa. So
Okay.
if you feel like you need to go over time, we have, for example, one slot after yours which is free. So we are going to
Okay,
put
you had the
and
discussion.
same for tomorrow and after tomorrow and after tomorrow.
Okay.
We have two classrooms in the afternoon, so we can split the room if we want to do that.
No.
No, I'm just telling you.
No, but not like not.
Will you be using a PowerPoint presentation or anything like that?
No, just the Blackboard, yeah. Okay, I'm ready to start.
Okay, so let's start. It's a pleasure to have Juan telling us about entanglement entropy.
Yeah, so it's a pleasure to be here. So I will be taking off from where Mark Van Ransdorp will have left. And no, I'm kidding. I'm joking. I will. The numbers were because we swapped, and initially he was going to talk the first week, and I was going to talk the third week. But now we have the other order, so I will start with the more basic things. So, of course, you all know information is very important, and you know that, for example, Shannon's thinking of classical information was very useful for understanding thermodynamics in a new way. And of course, quantum mechanics now will have to do with quantum information. And all physical theories, in some sense, are processing information in some way. You give some information about the experiment you are trying to do, and then you get some information out. So they are about information. Now, one could go over the top and say that physics is information. That might be true, but we don't know. Certainly, our physical theories have a little more input on how precisely we process this information. But something that has been very productive and useful has been to think about the constraints that information places on physical theories. Of course, the concept of entropy is a very clear example of that. But thinking more specifically about quantum information and how quantum information is stored in relativistic quantum field theory and also in quantum gravity it's very important, and understanding it in detail has led to some progress. And so my talks will be mainly about this topic, so how quantum information is stored in the theories we know about, in the theories of relativistic quantum field theory. And first I'll talk just about the case of relativistic quantum field theory, and then we'll talk a bit more about quantum gravity. So examples of results, very concrete results that have been obtained using this thinking of how quantum information is encoded in relativistic field theories are, for example, the C and F theorems. Then going to the case of gravity, so thinking about clearly about the black hole information problem requires you to understand, if you're going to solve the black hole quantum information problem, you need to understand some details of how quantum information is stored, and maybe by thinking about those details, you can even rule out some scenarios. Okay, quantum information, or constraints of information, might have something to do with the emergence of gravity, and certainly information constrains the organization of the state. So it's important. So states in quantum field theory are organized according to the normalization group flow. And thinking about this in a quantum mechanical way involves understanding how quantum information is stored in the state, and this has been fruitful to try to understand. Okay, so physics from information. Well, I said that you can go over the top and say that physics is all about information. I will not do that. But on the other hand, if you there seems to be some indication that thinking about gravity, for example, in terms of the Lagrangian as we usually think of, or thinking in terms of giving a formula. So Lagrangian gives you a formula for the dynamics of the theory, and you can alternatively give a formula for the entanglement entropy, so a concept I'll discuss later, but the area formula for the entanglement entropy seems to give rise to the same equations that the Einstein-Lagrangian gives rise to. So this might be more in Van Ranslog's lectures. Maybe I'll say a few things about that. And that's not a complete equivalence yet, but something that might develop into a complete equivalence in the future. Now, regarding this issue of whether whole physics is information, I encourage you to read Wheeler's article on it from bit, if you've never read it. So, but I don't have anything new to say. But if you want something over the top, you can read that. He has this picture of a big U. This is the universe. It's very small in the beginning and big here. And we are here looking at the universe. And we create it by the things we look. So the beginning of the universe is because we ask questions. We have questions about the universe, and by the questions we ask, we create what we see. That's, for me, maybe over the top, but maybe that's what will develop. Certainly Wheeler was right about many things, and so maybe he's right about this too. Okay. So but the first... so what we'll discuss here will be mostly, at least in the very beginning, will be mostly about entropy, about computing various kinds of entropy, and properties of entropy, of quantum entropy, and mainly of subregions, so mainly entropy of subregions in quantum field theory. Should I write bigger, or everyone can see? Good. And also the concept of so-called relative entropy. So that I'm just giving entropy. And then how this can be used in quantum field theory and gravity. So that will be the topic of these first few lectures. And depending on how we go, we might say some other things. So first, I'll talk about some basic concepts and relations. So basic concepts and properties of relative entropy and so on, and entropy, quantum entropy. And a reference or a book you might want to read on this is one by Oya and Betts. It has it's a book, so it's called Quantum Entropy, and its use, and contains many of the things. And if you want something online, you can find a review by Vedral, which is has this number. It's also a nice review. Okay, so now in quantum mechanics, the basic concept is the density matrix. So normally, in all these books, when they talk about the state, they typically think about the density matrix. And in the particular case that the state is pure, that comes, then we have that rho is equal to psi. So normally in quantum mechanics, we think of psi as the state vector. But you might, in these books, read that the state is really specified by density matrix, and that's the more general description of the state. Okay. So then once you get the density matrix, there is a notion of entropy, which is the von Neumann entropy, which is minus trace of rho log rho. And this von Neumann entropy is a measure of how much you don't know about the quantum state of the system. I mean, of course, in quantum mechanics, you cannot know everything. So even if you had the state with its complete characterization like this psi, you cannot predict the outcome of some experiment, right? You still have some randomness. But this von Neumann entropy measures the extra randomness that you have beyond the one you have in quantum mechanics. Okay, so you can if you had a pure state, then this entropy defined this way would be 0. And then you have determined your state as much as you can determine it by the rules of quantum mechanics. Okay, so, and of course this formula, when rho is a diagonal matrix, reduces to the usual Shannon entropy, so S, which is sum over I pi log of pi, and I'm sure you've seen both of these formulas in your courses on statistical mechanics. Of course, in this case, for this particular state, S is equal to 0. Okay, so now another concept that will be useful is the concept of relative entropy. So here in this case, we're given two states or two density matrices. So we have rho and sigma. Okay, so we could have the system described by density matrix rho and the system described by the density matrix sigma. And this concept called the relative entropy depends on both density matrices, and is by definition. So this is just the definition. Is trace of rho log rho minus rho log sigma. Okay. So these are matrices, so this rho and sigma do not commute, so this is defined in this particular way. But of course, you can calculate the logarithm of the density matrix, then multiply by rho, and actually compute this quantity. And now, it might be that you get infinity, so there is a possibility to get infinity here if, for example, sigma has a 0 eigenvalue at the position where rho has a non-zero eigenvalue, right? For example, imagine they are diagonal. Even when they are diagonal, you can have the possibility that you have an infinity, okay? And well, in that case, we define it as infinite, so no problem. Okay, so that's a definition. And in order to gain some intuition about the definition, one can think of the particular case where sigma is equal. I'm not going to write down the normalization constant. Of course, these density matrices are normalized, so that yeah, perhaps I should have said already here that we always have that trace of rho is equal to 1. Okay. Yeah.
Maybe a very silly question. Is there only one sigma on the right-hand side of it?
Yeah, I should also have emphasized that. This is not symmetric under interchange of rho and sigma. There's only one sigma. That's a good question. So the next remark will try to make that a little more natural. So imagine the particular case where sigma is proportional to e to the minus beta h. So it would be the sigma that corresponds to a thermal system, right? So you imagine you have a thermal system. And so in this particular example, for this particular case, then S of rho and sigma just becomes equal to the difference in free energy, the difference in free energy between the state characterized by rho and the state characterized by sigma. And you can check this. So in other words, so you'll have so the free energy is E minus T times S. So there is a term that involves the expectation value of the energy, and that's this first term, right? So this first term is so here when sigma is that particular expression, then this logarithm of sigma becomes just h, right? Minus h. This minus becomes a plus, and that's the expectation value of the energy, right? So that's the energy term. So let me call it the expectation value of the energy. Then this term is just minus the entropy, right? Up to, well, there are factors of beta I'm setting to 1, but so there is a beta here. So this is beta E minus S. So that's in the state characterized by rho. And then you can subtract the same things in the state characterized by sigma, right? And those terms really give you essentially 0 once you normalize this sigma properly. Okay, so if we normalize this sigma properly, then there would have been an extra term here that would not have been the Hamiltonian exactly, but there would be an extra shift, and that shift is precisely cancelled by evaluating E minus t times S with this particular density matrix. Is that clear? No? Should I do this more explicitly, or maybe you can do it as an exercise too? Should I do it or not? No. Yeah. So you can do it as an exercise. Now, so the point is that now this expression really is the expression for the difference in free energy that you would have for a system whose equilibrium state would be given by sigma, right? So if you had such a Hamiltonian, if you are able to choose whatever Hamiltonian you want to pick, you can choose a Hamiltonian such that the Hamiltonian is the logarithm of this sigma, and then this expression would be just that difference in free energy for the Hamiltonian you've chosen, and that's so that's the case. Now, from this discussion, it suggests that well, what should be the rho that minimizes this relative entropy? What would be the rho that minimizes this difference in free energy? Yeah, that's right. So the equilibrium state is the one that minimizes the free energy. And so you expect that if you take any other state, the free energy should be bigger, right? And therefore, the rho that would minimize this would be exactly equal to sigma, and so on. So in fact, you can prove that for any density matrices, so S of rho and sigma is bigger or equal than 0 for any two. I recall that sometimes it can be infinite, but that's fine. That's consistent with this inequality. It's always bigger or equal than 0, and it's equal to 0 when rho is equal to sigma. And it's not, so you can somewhat easily show it for diagonal density matrices, and if you think about it a little more, you can also show it for non-diagonal density matrices. Now, okay. So a property that is sometimes used related to this is the first law. So there is so you know the first law of thermodynamics that says that the change in entropy is equal to the change in energy, right, up to a factor of beta. And you can think of that as just demanding that the free energy is minimal. So when we just make a small displacement, we can only increase the free energy. Therefore, any small change to first order should not change the free energy, and to higher order, it should only increase the free energy, right? So if we think of this as a function of rho, so in the space of all possible rhos, of course, that's a very multidimensional space. So we have sigma here, and so here we'll have a minimum, and then it should increase. And that implies that we make a small variation. So if we change rho, if rho is equal to sigma plus some delta rho, then we will have that that delta S, so the difference in entropy. Yeah, so we'll have that. What we will have is that this. Due to the fact that it's minimal, first order variation of this should be 0. And this is the entropy minus the energy, in where the Hamiltonian is essentially given by the log of sigma, right? And this is sometimes written as delta S is equal to beta. Well, people sometimes put here a factor of 2 pi. Ignore the factors of 2 pi if you don't like them. Times k, times delta k. Where k is just the Hamiltonian. So usually in this context, people define matrix k, which which is just simply the logarithm of sigma. This is just by definition the logarithm of sigma, and it's called the modular Hamiltonian. I didn't invent the name. I don't know why it's. So it's basically the Hamiltonian that would correspond to viewing sigma as a thermal density matrix, and by convention we choose the temperature to be 2 pi. So ignore the factors of 2 pi; they don't like them. But this is sometimes called the entanglement first law, or should be called the this relative entropy first law. It becomes an entanglement first law when we get rho and sigma from thinking about entanglement, and we'll come that to later. But this is a relationship that has been useful. And perhaps I should also rewrite this relation. So the relation that says that this is positive can also be rewritten as saying that, again, 2 pi delta of the, let's say, expectation value of this k is bigger or equal than delta of s, where this delta is an arbitrary difference, not an infinitesimal difference, but an arbitrary difference. This is just the same as this equation for the free energy. The difference in free energy, so we said that this was bigger or equal than 0, and all I've done is to reshuffle the terms in such a way that we get this relationship. So these are completely general relationships. And okay, so this relative entropy should be thought of as some kind of distance between rho and sigma. So sometimes people call it a distance. It's not very good to think of it as a distance because it's not symmetric. So distances are normally symmetric, but if you read the reviews, they call it a distance. Probably not a good name, so maybe I shouldn't even say that. I should call it a distance. So it's a measure of the distinguishability, or the distinguishability of between rho and sigma. So imagine that you are looking at a system, some random system, and you are trying to guess what let's do this classically first. So let's imagine we have a classical system, which consists of, there are some variables. For example, a coin that I can toss, and it can be either heads or odds, and I'm trying to figure out what the probabilities are. So what the method for determining the probability is to toss the coin n times, right? And then say that the probability of the coin having the value I, so the value I means up or down, so in this case there are only 2 values, right? Will be equal to the number of times, so number of times that I appears divided by n, right? So it's just the frequency of the ith result in a specific throw of the coin, so that we threw the coin n times, okay? So that's one thing you could do, and that defines some pi. And in this way we get some pi, but imagine that the true distribution of the coin was not the pi that we got in this particular instance when we did the experiment with n times, but it was actually qi, okay? Right? So the idea is that so you would like to ask, well, how easy is, so of course if we would like to understand how improbable the result pi different from qi would be, okay? And you can calculate how improbable that result would be. You can think about this, and it turns out that the probability of getting a particular qi upon throwing the coin n times is going to be proportional to precisely this relative entropy of P and Q. Okay, so Q is the true distribution. P is something that could have come out of doing it n times, and this. Sorry, I forgot the factor of n here. Okay. So if you throw it n times, then the probability of getting confused between P and Q will start decreasing, right? As you throw it more and more times, you will be less likely to be confused. Okay. Now it's asymmetric, okay. So let's try to understand this formula a little more and why it is asymmetric. And so imagine that P is equal to a fair coin. So this is usually. And Q is equal to, so this has that means that the probability is 1/2, 1/2, okay, for the up or downs. And then Q is an unfair coin. So Q is a completely unfair coin, so always heads. So Q is equal to 1, 0. Okay. That's too small. Okay, well. Okay, so first one is an unfair. This part, last part was too small. Yeah, but I should get trained to. It looks big to me. Okay, so suppose we have these two cases, right? So then, now in this case, you can go back to the formula, and what do you see that what's S for this case? What's relative entropy? Infinity, I hear, yeah. So in this case, it is infinity. So let's try to understand this infinity. So this is saying that I will never, ever, ever confuse this P if the true distribution is Q. Okay, I will never, ever get this P. Okay. So what does it mean to get this P? It means that you threw the coin n times, and half the time was heads and half the time was tails, right? But if the true distribution is always heads, it's impossible to get half the time the wrong value, tails. Okay. So that explains why it's infinite and why it's reasonable that we get this infinity. Now we can do the other example. So we could do P is the unfair, right? Heads, and Q is even. Q is fair coin. Okay. So what do we get for relative entropy in this case? Well, this is a little more complicated. Well, if you do it, you can do it as an exercise and you will get log 2. Okay. And we get here. So in this case, in this particular case, this probability will be 1 to the 2 to the n. Okay. So now let's check that this is reasonable, right? So let's say we have a fair coin, right? So we have a fair coin that has the same probabilities of being heads or tails. And you threw it n times, and it turned out that the n times showed up heads, right? So what's the probability of that? That's 2 to the minus n, and that's indeed what this formula is saying. So you might get to the wrong conclusions about the probability distribution with this very small probability. Okay, very good. So that's just this definition. I said this in detail just so that we understand the definition, and also because this is usually said in the wrong way, the wrong order. Not usually, maybe some people said in the wrong order. Okay, so now, so enough with the relative entropy. Now, subsystems, okay? So imagine that, let me see. Well, so first let's talk about entropies of subsystems. So that's so in this case, a simple situation for this is to imagine that H is some Hilbert space where we take it to be a direct product of two Hilbert spaces for subsystems A and B. And this will be the structure of the Hilbert space if you imagine that you have two spatially, let's say, separated systems, like a bunch of spins here, physical spins here, and another bunch of physical spins on the other side. So here the full Hilbert space is the direct product of the two Hilbert spaces. So you should imagine as two decoupled systems, or that are initially separated in space, or separated because they don't interact, or whatever reason they are separated. And then we can think of the Hilbert space in this way. And if we can separate the Hilbert space in this way, we can take the original density matrix that is a matrix in the original Hilbert space, and we can calculate a reduced density matrix, rho A, which comes from taking the trace over the subpart of the Hilbert space HA of the original density matrix rho. Okay. Is it clear how we are defining this? Have you seen this definition before, or should I go through it a little more in detail? Who wants me to go through in detail through this definition? It's important it's crystal clear to you what we are doing when we do this. Yes or no? Who wants more details? No one wants to say they want more details. Okay. Okay, good. So how do we do this? So we choose a basis EI of the Hilbert space here, and let's say Wj. So these are some states in the two Hilbert spaces. The states of this Hilbert space are labeled, we can choose a basis, which is EI times Wj, right, where I runs from 1 to the dimension of A, j runs from 1 to the dimension of B. Okay? The dimension of this is the sum of the dimensions. No, the product of the dimensions, right? The dimension of this is the product of the dimensions of A times B. And so the density matrix then, normally density matrix has two indices, alpha and beta. But in this case, each index alpha is really these two indices, right? So we have rho of I and j, and I prime and j prime. Okay, so that's the total density matrix. After we write it in these spaces, it will have this index structure. This is a density matrix in subsystem A. So this should have, which indices should it have? I or j or alpha? Who thinks the indices of this density matrix should be j? And I? Oh yeah, the problem is I good, we are paying attention. I really needed to give more details because I wrote the wrong formula. Okay, so indeed we have indices I and j. Sorry, I and I prime. And this is the sum over j of rho I prime, sorry, ij, I prime, j. Okay. Maybe I wrote it too small, but so it's I prime. Those are the indices of the Hilbert space A, and we're just summing over the B1. Is that visible to everyone? Okay. Now we'll continue discussing these entropies of subsystems, but I would like to now make a point regarding relative entropy, so a particular inequality that is very important and somewhat difficult to prove. So I will not prove it. Which is that if you start from two density matrices, rho and sigma, so now we'll combine the two concepts. So we had two factors in the Hilbert space, and we'll go back to relative entropy where we have two density matrices. And now from these two density matrices, we can construct, through tracing out B, the density matrices rho A and sigma A. Okay. So these were the density matrices that we have if we look at the whole system, right? And now we have the density matrices of just a subsystem, so this is subsystem A. And we could calculate the corresponding relative entropies, rho A, sigma A, smaller or equal. Oh, sorry. And we can compare this to the relative entropy of rho and sigma. And the important thing is the inequality between these two. Now, recall, just to remember which direction the inequality goes. Relative entropy is a measure of how different the two states are, right? Now, if you only look at a subsystem, right, let's say at a part of the state, part of the degrees of freedom, do you think they are going to be more or less distinguishable? Less, yes? So everyone will think there will be less, and indeed that's what happens, and you can prove this inequality mathematically, so giving more credence to the idea that this is a good measure of the distinguishability of rho and sigma. Okay, so this is an important inequality that is quite non-trivial to prove for non-commuting matrices, and there are others that derive from it. So we'll discuss the others later. But I guess that intuitively should be true. It's clear. Okay, so now we go back to the discussion of the entropies of subsystems. And let's discuss. So imagine that rho is a pure state, right? So rho could be pure. But if we... Okay, so let's consider the following situation. So imagine that you have a bunch of spins. So this is subsystem A and subsystem B are here. Two separated, let's say some spins here, some spins over there. And we have some rho in the total Hilbert space, which is pure, so the entropy is 0. So then can we, if we compute the entropy of subsystem A, could that be non-zero? Oh, sorry. First I need to define what entropy of subsystem A is. So the entropy of subsystem A is just the von Neumann entropy of the density matrix of associated to subsystem A, right? So we start with the full density matrix, and this is defined even if rho wasn't pure. So in general, so this is a general definition, whether rho is pure or not. So you can define the entropy associated to subsystem A as the trace of this reduced density matrix defined in this way. Okay. Similarly, we could define the entropy of subsystem B, which is a similar construction, but where we now trace out subsystem A and we keep subsystem B. And sometimes the total entropy of the density matrix rho, sometimes we are going to write it as A union B. Okay, so that we put together the spins in subsystem A and subsystem B. Okay, we define this as A union B. Usually, also in relativistic quantum field theory, usually we're going to take A to be a subregion of space, and then it becomes really the union of the regions geometrically. But well, in general, it's the union of the two, and this is just the usual entropy that we defined before for the density matrix rho, original density matrix rho. So now there are a bunch of inequalities that hold. Okay, so one is this subadditivity property, which says that well, first of all, let's do an example, and then we'll discuss the inequality. So if rho is pure, then the entropy SA might still be non-zero. So you could have a situation where this entropy is non-zero, even though rho is pure, right? What's an example of a situation like this? EPR, yes. So if you have two spins in an EPR pair, then this entropy will be log 2 for each of the spins, but the total entropy would be 0. Okay. And then, well, so that was an example. And in these cases where rho is pure and we have a non-zero entropy, we assign this entropy to entanglement. So this entropy can only arise from entanglement. And it is sometimes called entanglement entropy. So when the original rho was pure, this SA of a subsystem is sometimes called entanglement entropy. But of course, if rho initially was not pure to start with, well, it could have been this SA might arise just from classical correlations. They don't have to arise through entanglement. Now, since this is sometimes called entanglement entropy, people then sometimes call everything entropies of subsystems always entanglement entropy, especially in the physics recent hierarchy theory literature. So you should be aware that it's not exactly what is sometimes advertised. Okay, so there is the von Neumann entropy of subregions defined in this way. When rho is pure, then we can think of that as entanglement entropy. Okay. Now, suppose that you have these two systems A and B. If rho is pure, what do you expect to be the relationship between SA and SB? Yeah, so in that case, they will be equal. And in general, there is a relationship that says that SA union B, this would be 0 for a pure state, but it might be non-zero for a non-pure state, is bigger or equal than SA minus SB, right? Bigger or equal than the difference, right? So this inequality says that if this was pure and this is 0, then indeed SA is equal to SB. But the generalization of that intuition to the non-pure case is this inequality that one can prove. And also there is an inequality which says that SA plus SB is bigger or equal than this, right? And one way to intuitively think about these inequalities, so you can think of A and B. I don't think this intuition translates into mathematical proof, but so you can have things that are entangled between A and B and things which are entangled between the outside world, right? And if you think about these entropies as counting the number of lines that you cut, then you get this type of inequalities. Okay. Now we can now, as we saw in this diagram, so SA might be non-zero because there is entanglement with some external system, right? But it could also be because there is some correlation between A and B, right? And there's a measure which is called mutual information. Mutual information, which is a measure of the correlation between A and B. So it's called, denoted by A and B. This now one is symmetric between A and B, and is SA plus SB minus SA union B. And by the inequality we wrote there, that's always bigger or equal than 0. And this is basically the yeah, it's the correlation. It could be quantum correlation or classical correlation. So it could be that you have a mixed state, but so you have coins that you throw, and when you throw, the coins are up in one side, they are down in the other side, completely classical. But that will give rise to a mutual information of this type. Okay, so one cool thing about this mutual information is that it bounds correlators. So it's related to it. Correlators in the following way. So imagine that we have, again, these two subsystems, and we have an operator OA in system subsystem A, and an operator OB in subsystem B. Then we can form these operators will have some expectation values in each of the. Of course, since they act on subsystem A, whenever I write expectation values, we are imagining we are doing trace of row O, right? And since this acts only on subsystem A, we could also write it as trace of row A, OA. Okay. It's too small again. Yeah, it gets smaller when you get further. It's just that yeah, it's this angle effect. Okay. I think we are discovering a new law of physics here. Very good. So now we are going to consider the connected correlation functions. So OA, OB connected, which are just simply the correlations, the really true correlations between A and B, where we subtract the expectation value of A and the expectation value in B. Okay? So that's the connected correlator. And the nice inequality is that this correlator can essentially be no bigger than the mutual information. So if you take OA, OB connected, you take the square of this, but you need to divide. Of course, you can always rescale the operator by some constant, so that we need to rescale out. So we'll define a norm of an operator to be the maximum eigenvalue. So that's the norm of the operator. Similarly for OB. So all these are things that are well defined in systems of finite number of degrees of freedom. Of course, if you have a field operator in quantum field theory, it's not well. We'll discuss that case when we come to it. So this is less or equal than the mutual information between A and B. Okay. And again, all these things are relatively easy to prove once you find the right trick, and in those reviews they're discussed. Okay, so these are some of the basics of entanglement and quantum entropy and so on. And there are many other things that one could say that I will not say. One could discuss Bell inequalities and how to make sure that they are not obeyed. When we divide the system into more than two parts, then the characterization of entanglement is a little more subtle, and I'm not going to discuss it. And another thing I'm not going to discuss is that some of this can be phrased not so much in terms of dividing the Hilbert space, but in terms of the operator algebra and thinking about algebras and subalgebras and so on, and assigning entropies to these algebras. And again, I won't discuss it from that point of view, but those are other topics I'm not discussing. Okay. So now we'll so all these were preliminaries. Now we'll get to applying many of these ideas to quantum field theories. And to apply them to quantum field theories, there are many subtleties. And the first one is that, well, the Hilbert space is infinite dimensional in quantum field theory, and so on. And we'll try to deal with these subtleties. And despite some of these subtleties, there are non-trivial statements that you can make. So some of these, most of these inequalities are, are proven for finite systems, so subsystems of finite systems. But in many cases, you can also prove them for subsystems of infinite systems, of infinite dimensional Hilbert spaces. It's a little more subtle, but it has also been done for many of these entropy inequalities. Yes. Go ahead.
Like general infinite dimensional Hilbert spaces or necessarily?
Yeah, so separable Hilbert spaces, but infinite dimensional. So they've been proven. But we will, the approach we'll take is that and that has been taken, that's been useful, is to think about the continuum field theory by first doing a lattice regularization, so that if you choose, in many cases, that will reduce to finite dimensional Hilbert space. And then you apply these formulas with finite dimensional Hilbert spaces. Sometimes you also need to discretize the target space and so on, right? Because even a harmonic oscillator has an infinite dimensional Hilbert space. So sometimes you need to cut off with some energy cutoff and so on to get the finite dimensional Hilbert space. Okay, so now we're going to start talking about entanglement or entanglement in quantum field theory. And the main point is that in quantum field theory, you can. Yeah, go ahead.
So in the quantum mechanics example, is any of these entropies more physical than the other, being more measurable?
Very good question. Yeah, I thought I was putting this. One feature of this entropy discussions and entanglement entropy is that, which is I feel it's an uncomfortable feature, is that entropy is not something directly measurable. And the point is the following, that anything that is directly measurable is some operator O, okay? And then the results of O, or the expectation value of O, are computed, for example, by computing the expectation value with some density matrix. But the entropies, and the properties of any operator of this kind is that it's linear in the density matrix, right? But entropy is non-linear in the density matrix, right? So if so, it looks a bit like an expectation value of something, but it's really something non-linear. So it's really not an expectation value, right? And so, in order to determine entropy, we would have to somehow determine the density matrix and then compute this log. Now, of course, in thermodynamics we use entropy. So you could say, well, I mean, experimentalists measure entropy with no problem. There is no problem. But how do they measure entropy? They measure entropy using the first law of thermodynamics. So they start from the system they have. They lower the temperature. They see how much heat comes out at each temperature. They divide the heat divided by the temperature. They sum this up. They go to zero temperature. And that's how they determine the entropy of a system, right? At least in principle. So that's how you do it in principle. And here you could imagine for a big system doing something like this. But that's something that you cannot do somehow for a system with a finite number of degrees of freedom. You have to repeat the system many, many times and do this. Anyway, so that's an uncomfortable feature of this entanglement entropy. But many nice results have been obtained by thinking about entanglement entropy. So it's been so far mostly a theoretical tool because it's cool from the theoretical point of view. It's, as we said, difficult to measure. Or, well, if you take this very in principle point of view, it's impossible to measure. But nevertheless, it's been useful theoretically. Now, what should you think in a situation like this? Maybe this is the wrong thing to focus on. But if you dismiss it completely, you are throwing away all the nice theoretical results you derive from it. Maybe there is some other quantity closely related that is more physical. I feel in some sense that relative entropy is a little more physical. Notice the close connection to the first law of entanglement and so on. Yeah, so maybe there is something better. Maybe there is some way to measure it. People have proposed indirect ways of measuring them, but they are not very general.
This first law of entanglement, is it a law or a definition? The way you were doing it was a definition.
No. What I did is, so I defined the. So one defines the relative entropy, And one notices that if you do a small variation of rho, then because it's always bigger or equal than 0, and 0 for rho equal to sigma, then for a first order variation, it's always stationary, it's always 0. So it's not a definition, it's something that follows from the definition and the properties of the, I mean, it follows trivially. You can immediately check it, please. Just exercise. Check that. I mean, you take that definition, you take rho equal to, let's see, is it still written there somewhere? No, I erased it. Okay. Just check it from the explicit definition. And if you try to check it, you will see it doesn't work unless you demand that trace of delta is 0, because you need to keep the trace of rho equal to 1, or sigma equal to 1. Anyway, so okay, so that's the point of it. This being mostly theory. So in quantum field theory, we can have so one important property of quantum field theory is that we cannot localize particles. So if we have, let's say, something like a single particle state, can we say that this single particle is localized within this very small region or not? And well, of course, approximately we can, right? In practice, we can certainly localize these boxes here and not somewhere else. But if we go to very short distances, then this is not possible, and we go to distances smaller than the Compton wavelength of the particle. Because we try to measure the particle, we create more particles, and so on. And so we cannot really localize particles. We cannot say a particle is localized to a very small region of space. But what we can localize in quantum field theory are operators. So operators are local. So we can think of operators acting on a localized degree of freedom, very, very tiny. And we have the intuition that the underlying degrees of freedom that are the fundamental dynamical variables of the quantum field theory are local. It's like having a local spin at each space-time point, at each spatial point. Okay. And so we have these operators which are local, and we can, in principle, localize these operators to finite regions, finite subregion. Now, this is a subregion in space. So this is a region in space. In space. Now, of course, we also have time. So we should think of, let's say, space. And then we also have time. So we were saying that we localize something. We can think only of operators which act somehow on this region of space. The operator might be non-local in this region. So you could have a Wilson loop, for example, a Wilson line that involves operators at different positions, or it could be the definition. You could measure an operator which is the product of a spin operator here times a spin operator here. That's perfectly allowed, right? What's not allowed is an operator which is measures a spin outside, right? That's not allowed. So you have all these operators. This is a subalgebra of the operator algebra, so you can multiply operators and so on. And furthermore, we know that if you have some other local operator here, the locality and causality in quantum field theory tell us that the properties of this operator are only determined by what's going on in the past Lycon, right? So all operators which are in this causal wedge are determined by the data on this surface. So we should think of this operator algebra we could think of it as a region in space. That's perfectly fine. But we could also think of all the operators in space-time which are localized within this so-called causal wedge. So causal wedge is you take the light sheets that come from the boundary of the region, you take them backwards and forwards, and you consider all the points in the interior. So okay. So if you had a field here and you had a causal, you have the second order equation, the values relativistic second order equation, the values of the field here would be determined by the values on this region. Very good. So I said that states are not localized. Now the vacuum is, of course, the vacuum is just a pure state. So if we took the density matrix of the whole of the vacuum, just that would have zero entropy. But if we consider two subregions, so just the fact that correlation functions, so let's say we have two subregions A and B. So we have a point x here and a point x prime here. You know that the expectation values of the field operator are non-zero, right? So these are non-zero. So this implies that through the bound that we were discussing over there, the bound on the expectation values of operators, there should be a non-trivial mutual information between these two, and in particular, there should be non-trivial entanglement entropies associated to each subregion. Okay. And because these expectation values can be very large when you take the points very close to each other, you realize that these entanglement entropies will have to be infinite. Okay. Now, strictly speaking, to apply those bounds, strictly speaking, the norm of an operator, of a field operator like this, is infinite for two reasons. One is very localized at the point, and the second is that the actual amplitudes of this field go from plus to minus infinity. So in order to say this a little better, you would have to integrate the field operator over some region, some small region R, and then put that integral in the exponent, right? So now we get something which is it has bounded eigenvalues, right? Anyway, if you want to apply that argument. But in any case, the final conclusion will be that we expect these entropies to be infinite. Okay. Now, so they are infinite, so something that is infinite is not so well defined. Another thing is that really the Hilbert space cannot, in the continuum field theory, cannot be separated into the Hilbert space inside the region and the Hilbert space in the region outside, the array complement. Okay, so this is not strictly valid in the continuum limit. So in the continuum limit, we cannot do this. And however, something we can do, and the typical approach is to do it in first do a lattice regularization. And then everything is fine. Okay, so then you can really divide the Hilbert spaces into the two parts. And then we'll remove the so the strategy is first do a lattice regularization, then calculate these entropies, SA, for example, and then identify the divergences that arise when the lattice regulator goes to 0, and understand them well enough so that you can remove them, right? So these calculations of entropy are somewhat similar to calculations of any other observable. Most observables we do in continuum quantum field theory. When you try to compute them naively, you get infinity, and you have to be a little more sophisticated to compute something that is finite. Okay, and so understanding the origin of the divergences is part of understanding how to get something finite out of these things. And the recent progress has been in trying to understand those finite pieces. Okay, so how much? When am I supposed to end?
1 hour.
Okay, yeah. Okay, yeah. Very good. So,
are all of the quantities that you wrote divergent, or some of them are already finite?
yeah, we'll discuss them. Yeah, so the relative entropy is already finite, and mutual information is already finite. But in order to see why it's finite, I'll need to that's the point I was going to try to explain here. So to understand why they are finite, we need to understand the divergences a little bit. And today, right now, I'm going to just state what the divergences look like, and then we'll probably discuss them in more detail in some more specific cases, just to understand why that is the case. So the result, so there is some epsilon will be the ultraviolet cutoff, could be the lattice spacing when we regularize the theory by putting it on a lattice. And So here we are considering a region in space. So let's say it could be a circle or it could be any shaped region in space. And we are going to calculate the entanglement entropy associated to, or the von Neumann entropy associated to this region. And the first result is that the divergences go like the area of the region, area of the boundary of the region, I'll say in a second, to the dimension of space-time minus 2. So this area is the area of the boundary of A. So the boundary of A is this surface here, right? So if space were two-dimensional, as in the blackboard, so we have 2 dimensions of space, 1 and 2, and in addition we have the time direction that I'm not drawing. So in this case, capital D would be 3, and this would be 1 over epsilon, and this area would be the length of this curve here. Okay, is that clear? Okay. So imagine you are in 1 plus 1 dimensions, right? So there is only one direction of space, so that I drew here. And then we have an region A is this interval. What do you expect this formula to say? What's the boundary of A? Are these 2 points, right? So we have 2 points. And when this is 2, this becomes a logarithm of epsilon. So in the particular case of D equal to 2, we have that S of A will have some divergences. The leading divergences will be the log of epsilon times some coefficient, some number, times the number of points in the boundary, number of points. The number of points would be 2 in this case, but if we had region A where this disconnected region of 2 intervals, right, we would have a factor of 4, right? But the idea is that these coefficients, so especially in this 2-dimensional case, is a universal constant we'll discuss later. In the higher dimensional cases, the coefficients depend more strongly on the cutoff, because if you rescale the cutoff, of course, this number gets rescaled. Here, since the coefficient is of a log, it has a more invariant meaning, okay? And we'll calculate it later. But an important point is that the divergence does not depend on the state that we have. So if we have the vacuum, we have this divergence with some number. If we keep the same regularization procedure and we consider a state which is not the vacuum, then we'll get exactly the same number, the same divergence. The finite pieces will be different, but the divergences are going to be the same. So this is, yeah. So here we are using so all these things are true in any relativistic quantum field theory. Okay. Yeah, you can have anything that is a quantum field theory. So this does not apply to gravity, for example. So gravity we'll discuss later. But if you have a theory that has gauge fields, matter fields, and so well, gauge fields is a little more tricky, but it also has this property. Yeah, it's a local quantum. So okay. So when I say relativistic quantum field theory, what I mean is a theory that is what we call local, not just causal, but local. That it has a local stress tensor. It's local in the sense that it has these localized degrees of freedom that exist at every point, and so on. So all the typical theories we consider in physics are of this kind. So the standard model is of this kind, and the theories that arise in condensed matter physics are of this kind, while the ones that are relativistic are of this kind. And those are the theories I'm discussing here. Yes? Sorry, yes. I'm discussing, here is for any state. So I'm discussing the divergences, and this is true for any state.
Is it also good for non-Lagrangian theories, like 3 times 0?
Yeah. So this is supposed not to depend on the Lagrangian. It's supposed to be something completely general. Now, in condensed matter physics, there is a lot of discussion of area law and so on, and when system can have an area law. But they're interested in the finite pieces. So they have a more, there is a UV cutoff, which is the atomic scale, and then there will be some finite piece, and the system could have an area law, could not have an area law, and it depends more on the system. Okay. Very good. Let's see, what was I going to say? So we have these divergent terms, And in general, there is a whole series of divergent terms with less and less powers of epsilon. So in 2 dimensions, it just stops here and then is finite. That's for d equal to 2. For d equal to 3, we also get only this term and then something finite. For example, for d equal to 4, we also get a term proportional to curvatures. Let me call them curvatures. It could be the curvature of the space where this is defined, or it could also be the extrinsic curvature of the surface, and so on. That is down by some powers of epsilon to the d minus 4. So for d equal to 4, this is a logarithmic term. Okay, and then we go to 5 dimensions. This would be a 1 over epsilon, and those would be the only 2 divergent terms. And then we'll have to go on and on. And there's been some characterization of this curvature term. So there could be here various curvature structures involving the various contractions of the extrinsic curvatures and the curvature of the ambient space. But I won't discuss them in detail. But all these divergences are essentially state independent. What I'm saying is not 100% correct, but let's say to first order correct, like many things we have to first. So there are sometimes some subtleties in these diversions that I want. Yeah.
Do you always get 1 over epsilon with d minus 2 and then d minus 4?
Yeah. So So here we can understand this evenness. Let's say if we think in terms of the extrinsic curvature, right? So you might wonder, why don't we get the term which is linear in the extrinsic curvature? The extrinsic curvature, K, would be proportional. Let's say if you have a circle here of direction length L would be of order 1 over L, right? But if we consider the vacuum of the theory, then the SA and SB should be the same, right? But the extrinsic curvature as viewed from B has the opposite sign. So a term which is odd in the extrinsic curvature cannot appear. Okay. So that's why you don't get here the term which is linear in the extrinsic curvature. We could have only 1 power of epsilon. So that gets rid of the odd terms which could only come from the extrinsic curvatures. And then Riemann curvatures and so on have two derivatives. So dimensional analysis together with this argument says that you have this even expansion. But of course, if the theory has some other mass scales and so on, they could also appear in here, and you could have a more complicated structure of divergences. This is the simplest situation where, let's say, you have a scale invariant theory. So when you have other mass scales, they could also, instead of a power of epsilon, you could get the power of the masses, and so on. And so you have something a little more complicated. But the basic idea is that whatever you have will involve, in this case, curvatures. In the most completely correct statement is that it will involve local operators evaluated on this boundary. So that's the most general statement. So when I said that there are some subtleties, I mean, in some cases, you need to have sublimiting divergences that involve expectation values of local operators on the boundary. They are not important for what we're going to say, so don't worry about those. Good. Now, the fact that these divergences are state independent implies that that will imply that the relative entropy is well defined. Okay, because the relative entropy, recall that, well, I erased the formula, but could be viewed as the difference in entropy between the difference in free energy, and difference in free energy is different in energy and entropy, right? At least for the entropy pieces, it's clear that we have something finite because we are subtracting two infinite quantities. And actually, the relative entropy is really finite. It's the thing that is best defined in continuum quantum field theory. It's relative entropy. The other thing that is finite is mutual information. So we have two regions. So we have, let's see, the definition of mutual information here for A and B. And if we have, this is region A, and region B is a disconnected region, so a region that is separated from A. Then you find that here in SA you have a divergence which is proportional to the area of A, right? And similarly for SB, and in S of A union B, we'll again get the area of A plus the area of B. So they will cancel. Those divergent terms will cancel in this difference. Okay? So that's something that is finite. So it's something better defined. Okay, well, yeah, also a subleading terms also, because, yeah, so the reason that they cancel is that, well, especially in this case of mutual information, they cancel even if we have, well, if we have curvatures, it's always the integral of some local thing here, and, well, we'll have the sum of the two terms, right? So these terms are not only, yeah, maybe you should have emphasized that, they are not only, well, state independent and it's the area, but this area is just some local integral over the boundary. So there is the boundary of region A, and we're just integrating square root of g over that boundary, right? So it's the integral of a local quantity along this boundary. And here again, we're integrating the curvature along the boundary. So the fact that it is this integral makes sure that they cancel. So there is some integral here, they cancel out. Okay, so I could finish here. This is a good place to stop, or I could go for 10 more minutes.
Why don't we stop and continue the discussion?
Good, yeah.
We have a discussion slot.
Yeah.
Very good lesson, Juan. But maybe first questions? Other questions? Not but half an hour.
So he'll give some more of his lecture, you think, in the discussion? Because I probably can't stay tonight. It's not going to be the whole second lecture.
No, maybe 20 minutes, half an hour, and then I think we'll probably stop.
Okay, that sounds good.
Full half hour and that.
Go down the stairs over here, one level, and then walk sort of that direction. You absolutely have an office.
Okay.
So do all the lecturers.
Distribution that you would guess from a limited number of terms. And so those